Totally. Yes. Let's see. What's your email address?
AALEVI@UCDavis.
Alexis? Cool. You've been added. All right, let's go ahead and get started. Just a couple things. So unfortunately, I wasn't really able to find another practice piece of information that I think is very applicable. Well, I should say, except for one. I did find one which I will post to our Canvas after class today. Sorry, one second. Let me just do this. Sure. But just in case you're curious where it is. It's on this. So this page actually, which is where I think most of the material from Dr. Babson, just the homework assignments are coming from. If you scroll down here, it's actually interesting because it's with the wrong textbook. But if you look down here at the 21B Thomas website, and you scroll down to where'd you go here? To the practice exam 2. I feel like this one has a fair number of questions which are of the same content. Set up an integral for the volume. Okay, maybe not that. But then for finding the y coordinate of the center of mass, that's certainly something you could be asked to do on this exam tomorrow. Or the volumes of revolution one, again, not super right on, but not bad practice for setting up. And then there's an arc length one. There's a work one down here. So there's a few good problems. I will definitely post this on our Canvas, but you can also find it on Dr. Fu's website. I'll post the solutions as well. I'm sure they're correct, although I have not vetted them, but they've been up so long that they have to be correct at this point. All right, so many of you, most of you, maybe all of you, have an exam tomorrow. Some of you might not. But those of you in Babson's class certainly do. So I guess I should first ask, do you have any questions from the practice exam that he posted? Have you looked at the practice exam that he posted? Should we go over it? Okay. So, and actually, well, that brings me to a question is, for this first one here, I have no idea what shape he's actually describing with what he's written here. So, let me write down some things here. 21B is 27th. So, the first question says, consider a 4-meter deep wedge-shaped pool with a rectangular top, 5 meters by 12 meters, and a triangular side. Yeah. Okay. All right. Interesting. All right. That makes sense. It's not, I mean, it's right, but it's hard to know that from reading it. So, okay. So it's 4 meters deep. Here's my 5 meters wide by 4 meters deep side. And then, or is this my gosh, I am so bad at this. And then, yeah, so this is the 12 meters. Okay. I guess that works. Like that seemed reasonable. Okay. Um, sure. Although who's to say why it has to be 12 meters on this side and why couldn't it be 5 meters here and 12 meters there? Anyway, let's look at the question. Find the work required to empty the initially full pool by pumping all the water out the top. The weight density of the water, W or omega, is 50 newtons per meter cubed. So our density, 50 newtons per cubic meter. And we're being asked to figure out how much work is required to essentially lift all the water. Right. I feel like this is set up very weird. No, okay, that's totally fine. Sorry, I'm just looking at this like, okay, yeah, that totally makes sense. All right, so we're going to calculate work. In general, work is force, aka weight, times distance traveled. And there's lots of ways to kind of think about setting this up. I usually like to think of moving up as increasing my y value. So I would probably think of the bottom part here as maybe y equal to 0 meters, all the way up to the top as like y equal to 4 meters. And then what we're essentially going to try to do is look at some slice of water that all has to travel the same distance. So it all has to be at the same depth. So hopefully my drawing doesn't fall apart here. But here's my slice of water. Want to look good. It's pretty good. Okay. So there's our slice of water. It doesn't look perfectly parallel because, I'm not the best drawer. But that slice of water is going to have some weight, and we're going to figure out how far it has to travel. So here's what we're going to do. We're going to say it's at a height of y, and the distance it has to travel is going to be 4 minus y. And now we really have to find the volume of our slice. So the distance, we're good to go. That's going to be 4 minus y. The force, on the other hand, the force, aka the weight of our water, is the volume of our water times the density of our water, which he's used omega for. So in this case, the omega part, that's just going to be our 50 newtons per cubic meter. Our volume, that's the part that's challenging here. That's where we actually have to do some work to figure out what our volume is. So, well, not too bad. This dimension is just going to be 5 here. So really we just have to find out how long this piece is. So I'd probably do something like this. So I'm trying to figure out, this is my slanty side right here. So down here at the bottom, I'm at a height of 0, and I've gone 0 from the side. And over here, over at the top, I've gone up 4 meters and over 12. Everyone seem cool with that? Again, I'm kind of thinking about this part here being my y-axis and this part here being 4 above my x-axis, like that. So just the side view of this wedge-looking pool. So we're trying to figure out how long that part is so we can figure out how much volume is in this slice. Okay, so let's find the equation of this line. My slope is 4 over 12. So my equation of my line is y equal to 4 over 12, or 1 over 3 times x. But I want to find out how long it is, which is how much horizontal distance it has. So really I should be saying that x is equal to 3 times y, which seems reasonable, right? If x is 0 at the bottom, our length is 0, right? We don't have anything. Whereas if x is 4, sorry, if y is 4 at the top, if y is 0, x is 0. If y is 4, x is 3 times 4, which is 12. Seems plausible. So that means our volume is going to be 3 times y times 5 times dy. 3y meters by 5 meters by dy meters. I like to check that to make sure that the units are making sense. It's a volume and it's meters by meters by meters. So I know it's a volume. So I think we're ready to set this up. So our work integral is going to be the integral of my weight, which is 3y times 5 times dy. I'm just going to throw it all in kind of messily. I'm maybe going to put the dy in a weird spot there, times my density, which is 50. I don't really need the units, times my distance, which is 4 minus y. And then the thing is full of water. Yep. So we're going to integrate all the way from the bottom to the top. But if it was, say, only filled to a depth of, say, like 2 meters, you integrate from 0 to 2. So make sure you read for that part because that part's usually going to determine your limits of integration. And then the rest of this isn't terrible. So I would certainly pull out the multiples 3, 5, and 50. So that's going to be 750 times the integral from 0 to 4. I have a y times a 4 minus y. So that's going to be a 4y minus y squared dy. And then the rest of this is not terrible at all. We integrate. So again, with these problems, usually the integration is the easiest part. The setup is usually really what is challenging here. So we're going to get 750 times 4y squared over 2 minus y cubed over 3 from 0 to 4. How much you want to simplify here is kind of at your discretion, depending on what you think your teacher wants to see. I might stop there if I was pressed for time. I might go one more step and plug in and say I've got 750 times 2 times 16 is 32 minus 4 cubed over 3 is 64 over 3. And then you could go further, but not. That's going to be 96 thirds divided by 6. So it's going to be 32 thirds times 750. And then 750 divided by 3 is 250. So you get 250 times 32, which is going to be what, like 8,000? Yeah. 8,000 watts. Joules. You can also say Newton meters, but joules is more correct. I'm looking for something. Water, that's something. If this was a question on the test and it was only written words and not a picture drawn, I might ask the instructor, like, how do you mean this to look? Because I feel like it's really open to interpretation. So for things where you have a shape that might not be super clear, ask for clarification if you can. Or hopefully it's described clearly. Because I felt when I was reading this, I was like, I have no idea what this thing looks like. I was finding it very challenging to figure out what it looked like. So thank you for helping me with that. Questions about this before we look at part B? Yeah.
Can you just say like for the initial work integral,
Mm-hmm.
can you just like say one more time? Like,
Yes. So my work so for my work integral, it's my volume times my density times my distance. So here's my distance from the top. Here's my volume, which is my 3y length here, times my 5 length here, times my thickness of dy. That's what that is. It's my 3y times 5 times dy. And then we're multiplying by density because volume times density is going to give us our weight. Yeah, so for water ones, with work for water or any fluid, it's always the volume of that slice of fluid that's all moving some set distance, and then multiplied by the density of that volume, multiplied by the distance it has to travel. All right, let's look at the second part here. There's an underground maintenance room at the deep end with a rectangular door that is 2 meters, that's very tall, that is 2 meters tall and 1 meter wide. So when the pool is full, the top of the door is under 2 meters of water. Find the force on the door when the pool is full. Okay. So fluid force due to pressure. And our door is, sorry, it was 2 meters tall, 1 meter wide. Does it matter that it's wedge shaped? Would the fluid force on the door be the same if it was a wedge shape over here? Or just a regular like cubicle pool or parallel pipette shaped pool? It's a good question. Does it matter if I have water down here or no water down there? I don't think it matters, right? Because when we're talking about fluid force due to pressure, it's typically equal to the depth that we're at multiplied by the area multiplied by the density. Because again, if we're trying to calculate force, we should be being measured in either newtons or pounds, in this case, newtons. So it should be a density, newtons per cubic meter, multiplied by cubic meters, so that the units we're left with are a unit of force or weight. So it's always good to think about what kind of units you want to end up with to make sure you're multiplying the right amount of things together when we're talking about force or work. For work, it's force times a length or a distance. For force, just force. I know that sounds kind of self-repeating, but that's what it is. Okay, so kind of like in the previous problem, we're again going to think about some thing we want at a fixed depth, because that fixed depth is either how far it has to go for a work problem or how much water is on top of it for a fluid force problem. So same deal. We're going to say down here at the bottom is y equal to 0. Up here at top is y equal to 4. We're going to pick a thin strip, right? The strip, because it's two-dimensional, it's not a slice that's 3 dimensions of water. And we're going to find we're going to say that strip is at a height of y, a depth of 4 minus y. But now the fluid force on our strip, well, again, the force is the area times the depth times the density times, that's it. Area times depth and density. All right. So the area of that strip is actually not terrible at all. It's 1 meter wide by dy meters high. So it's 1 meter times dy meters. The depth is 4 minus y meters. And the density is still 50 newtons per cubic meter. So just to really, again, I wouldn't probably write this if I was taking the test, but I'm really just trying to emphasize here that my units work. My meters times meters times meters cancels out my meters cubed, and I'm going to get 50, or I'm going to get newtons as my final unit of measurement. Why would that be dy meters? So again, because we're talking about how much fluid force is on a particular amount of area at a fixed depth. The problem is this entire door is at different depths. So sorry, just the question was, by the way, why would that be dy meters high instead of 2 meters high? And the answer is because we want to think about the fluid force on this little amount that's all essentially at the same depth, because our dy is very, very, very small. The 2 we're going to use to help us find the total fluid force by adding up all the fluid forces. So this one strip right here has that much force acting on it. And then to find the total force, we're going to add up all the forces from as low as strips down there to as high as strips up here. So we should have the integral from 0 to 2 of this amount here, which I'm going to rewrite as 50 times 4 minus y dy. I'm going to compare my work to his just to see. Nope, looks good. Looks just the same. So then again, integrating this is not terrible. You get 50 times 4y minus y squared over 2. From 0 to 2, you plug in, you get 50 times 8 minus 4 over 2 minus 0. And then you're going to get 50 times 8 minus 2, which is 50 times 6, which is 300. 300 watts? Newtons. Yeah. Because it's still in the pool. Same pool, right? So this is part B of the same problem, right? In the same pool, there's an underground maintenance room at the deep end with a rectangular door. So we're on the deep end of the pool over here. So this is the deep end where, right, this width is still 5 meters, this length is still 12 meters, and this depth is still 4 meters. So then, right, this door here is at a depth of 4 minus y meters, where y could be as low as 0 and our depth is 4 meters to as high as 2, or our depth is 4 minus 2, which is also 2. So again, for problems like this, finding a strip or a slice that is all at the same depth or all has to travel the same distance is kind of vital. Question? Because Right. So it's not the height of, it's not the height, it's the amount of water that is sitting above it. And since the pool was full, right, the amount of water sitting above it is this, right? All of this, right? All of that there, that's all water that is sitting above that strip right there. If they had said the pool was only full to a depth of say 3 meters, then we would be doing the same interval, but we'd have a 3 minus y instead of a 4 minus y. All right. Other questions about this one? If we have time at the end, we will come back and we'll try to make up another one that's just as fun. It's easier to describe though. All right, let's look at this next one, which looks to me considerably less terrible. Number 2, consider the initial value problem. dy dt is equal to t squared y with y of 0 equal to 5. I say to find y of 3. So let's point out when something says it's an initial value problem, it means you have a differential equation, probably separable, and you have some initial condition which will allow you to solve for whatever constant pops up after we integrate. So step 1, separate your variables. So if I've written dy dt on the left side here, then my y's have to come to the left and my t's have to go to the right. So I'm going to write this as 1 over y times dy equal to t squared times dt. Then we're going to integrate both sides. So the integral of 1 over y is equal to the integral of t squared dt. When we integrate this, you get the natural log of y equal to t cubed over 3 plus c. Technically, it's the absolute value of y. I'm not terribly concerned though. So here's what I want to point out. This is not the moment to plug in 0 for t and 5 for y and solve for c. Because if you solve for c, you're going to get c equal to e to the 5th power. And then you're going to have to like carry it along with you as you do all this other work. So let's wait until we see our constant, until there's a little bit less work to do on this side over here. So let's exponentiate both sides and say that e to the natural log of the absolute value of y is equal to e to the t cubed over 3 plus c, which I would rather write as e to the t cubed over 3 times e to the c, which I'd actually rather write as e to the t cubed over 3 times a, where a is e to the c. So now we've got e to the natural log of the absolute value of y, and the absolute value does get to go away now, is equal to a times e to the t cubed over 3. And now it is much easier to find your constant a, because if you plug in t equal to 0 and y equal to 5, bless you, you're going to get 5 equal to a times e to the 0, which means a is just 5. So our general, or I should say our particular solution to this differential equation, not the answer to the question, but the solution to the differential equation is y is equal to 5e to the t cubed over 3. Which is exactly the way your instructor has written in the solutions. And then to solve the question, well, y of 3, we're just going to plug in 3 for t and get 5 times e to the 3 cubed over 3. And 3 cubed over 3 is 3 squared, which is 9. So you get 5 times e to the 9th. And that is the best answer to your question. I will point out, just to really convince you that this is the way you should do it, you could make this harder on yourself. You could say, I don't want to do it that way. I'm going to say natural log of y equals t cubed over 3 plus c, and find c right now. So I'm going to say natural log, I think I said e to the 5th before. I was mistaken. It was natural log of 5, apologies. Natural log of 5 equals 0 plus c, so c is equal to the natural log of 5. This will work, it's just going to be more work. So now if I go back here and say the natural log of y, and I am going to ignore the absolute value because your instructor does, and we can. So if you want to do it this way, cool, but then we have to be extra careful when we're doing the rest of this. So then e to the natural log of y equals e to the t cubed over 3 plus natural log of 5 in the exponent. But then we're going to break that up as e to the t cubed over 3 times e to the natural log of 5. And then e to the natural log of 5, that's equal to 5. So we get 5 e to the t cubed over 3. I'm not saying it's terrible to do it this way. I'm just saying it is a little more work. But either way, you should get to this particular solution. And then you can plug in whatever thing they've asked you to plug in to answer the question. But again, if it were me, I would do it this way, not the other way. Any questions about that one? That one seems pretty straightforward, yeah. Like from here to there?
No.
Oh, sure. So when I see this equation, so I will point out two things. Two things, maybe. Yeah, two things. So first and foremost, when you have a differential equation and you want to separate variables, because that's the only way we know how to solve them in this class, which is great, you need dy dt by itself and everything else on the other side. And then after you've gotten there, if it doesn't start there, which it usually will start there, but after you've gotten there, then the only things you're allowed to do after that are multiply and divide. You cannot do anything else. You cannot add, you cannot subtract. So if you have weird stuff on the right-hand side, you might need to like factor something out. Like for example, if I gave you this differential equation, dy dx equal to x squared plus y times x squared, the only way you can separate variables here is first by factoring out an x squared and saying, okay, dy dx is equal to x squared times 1 plus y. And then you can divide both sides by 1 plus y and get 1 over 1 plus y and multiply both sides by dx to get x squared times dx. Similarly here, I'm dividing both sides by y or multiplying both sides by 1 over y to get 1 over y dy dt equal to t squared, and then I'm multiplying both sides by dt to get 1 over y times dy equal to t squared times dt. So that's how we separate variables. So we're always, if you're writing your derivative on the left, the top thing, y, has to come to the left side, and the bottom thing, t, has to end up on the right side. Yes, only multiplication, like, so for this one here, right, it couldn't be like adding or subtracting x squared or yx squared to one side. I have to multiply or divide. All right. Let's look at the next one, which looks really fun. So part of taking this exam is keeping your cool, right? These problems are going to look hard at first, but they're not going to be that terrible. Probably. I mean, I would hope. Consider the region bounded above by the curve y equals 1 minus x squared, and below by the x-axis, which is just y equals 0, and between x equals -1 and x equals 1. You don't have to, but I really think it's worthwhile to draw this. So it's a downward opening parabola. It's got x-intercepts at 1 and -1, and a y-intercept at 1. So it's not quite a semicircle, but it looks kind of like that. So there's the region that we're looking at. Above, bounded above by 1 minus x squared, below by the x-axis, yes. Find the area of the given region. Okay, so the area should be not too terrible. It's just the integral from -1 to 1 of our function, 1 minus x squared. If you like, it's 1 minus x squared minus our bottom function, which is 0. Right? When you're finding the area between two curves, it's the integral of the top curve minus the bottom curve. Just in this case, the bottom curve is the x-axis, which is y equals 0. And that's not bad at all. I will point out, if you really wanted to, you could use a trick to make this slightly easier to calculate. I don't think you need to. In fact, I'll do it this way first. It's going to be x minus x cubed over 3 from -1 to 1, which is going to be 1 minus 1/3 minus -1 minus -1/3, which is going to be 1 plus 1 minus 1/3 minus 1/3. And 2 minus 2/3 is 4/3. Or you could have noticed that this function is even. And so if you'd wanted to, at this stage right here, you could have instead written it as 2 times the integral from 0 to 1 of 1 minus x squared. and then gotten 2 times x minus x cubed over 3 from 0 to 1, which is 2 times 1 minus 1/3, which is 2 times 2/3, which is 4/3. Either way, yeah.
Explain the last part.
Yes, so you mean like starting with this right here. So what I'm observing is that this function has symmetry about the y-axis. So what I've done, instead of finding the area from here to here, I have found the area from 0 to 1, just this right side, and then I have doubled it. So that's what's happening there. If you notice your function is even and it's going from negative something to the same positive something, then you're allowed to cut the interval in half from 0 to the something and then double your result. It just makes it easier because like plugging in the -1 over here it's easy to make a mistake with your signs over here. So just be extra careful here. All right, find the center of mass. So this problem is giving you something already. You should already know what the x coordinate of your center of mass is. Everyone should know just by looking at this shape that the x coordinate of your center of mass is 0 because of symmetry, right? This shape is symmetric about the y-axis. It has a center of mass that is in its dead center x coordinate. Now, it is not symmetric the other way, right? If you look from top to bottom, you definitely have more area on the bottom, less area on top. So to find our y coordinate, we actually have to calculate things. So to find our y coordinate of the center of mass, it's going to be the moment around the x-axis divided by the total mass, or area, because it's area. It's a centroid, not a center of mass, but same distance difference. Yeah, so we're really finding the centroid here because there is no density to speak of. Right? The problem doesn't say with a density of anything. So center of mass is just the centroid. All right, so to find the moment around the x-axis, oh, that's the worst one. That's the one we have to use this funky formula that I sometimes forget, actually. Yeah, let's see here. So to go around the x-axis, to find the moment, we're thinking about this strip having all of its mass centered at the middle of it. So our moment around the x-axis is going to be the integral of our lever arm length, which is how far it is to the axis. So that's just going to be half of the function, 1 minus x squared. So it's going to be 1/2 times our function, 1 minus x squared. That's our lever arm, or the distance to our strip, or to where our strip's mass is all centered, multiplied by the area of the strip, our height times our width. The more general formula being that the moment around the x-axis is 1/2 the integral of the top function squared minus the bottom function squared. It's just in this case, our bottom function is 0. But it's exactly what we've got. We've got 1/2 times f times f, or 1/2 times f squared. And our limits of integration should be from -1 to 1. And this is an excellent opportunity to use the fact that we have an even function again. It is still even. And we can rewrite this as 1/2 times the integral from -1 to 1 of 1 minus x squared squared. I probably should just that is the least helpful way of writing that. Right? I'm not going to integrate it like that. I should have multiplied it out. That was just a waste of space, really. But then we're going to rewrite it as, watch carefully, 1/2 times 2 times the integral from 0 to 1. And if we multiply this out, it's going to be 1 minus 2x squared plus x to the 4th. And we definitely know it's an even function. You can either know it's even by noting that it's a polynomial whose powers are all even, or you could literally plug in -x for x and see that you still get the same function. Right? If you replace every x with a -x, nothing changes. That means it's even. So now we do the integral. We get x minus 2x cubed over 3 plus x to the 5th over 5. But if you're going from 0 to 1, that's great because you're just going to get the coefficients. 1 minus 2/3 plus 1/5. And I really would not take the time to simplify that unless I had all the time in the world. I'd done everything else. Right. So I should point out we're not nearly done though. Make sure my answers are correct here. Yeah, that looks good. Okay, cool. Yes.
Why did the bounds change?
Again, so I did the thing I said I was going to do, which was from here to here, I cut the integral interval in half and then also doubled the result. But I only got to do that because I have what kind of function? Even function. It is worth doing though, I think, because otherwise you're going to be writing 1 minus 2/3 plus 1/5 minus -1 minus 2/3 minus -1. It's a bit messy. And again, not that you can't do it that way, just it's trying to make our lives a little bit more simple. All right, so I need to be extra careful here because I haven't finished this problem at all. First of all, even if this was the right answer, which it's not because I have to divide by something still, I still have to write my center of mass as a coordinate. So my center of mass should be x bar comma y bar, which is going to be 0 comma this number, which I know I just went on a long rant about not simplifying it, but now I'm going to simplify it because I have to divide it by that. So that's going to be 15 over 5. 15 over what, James? 15 over 15 minus 10 over 15 plus 3 over 15, which ends up being 8 over 15, which hopefully is correct. It's always good to check your work along the way if you can. Obviously, that's not an option when you're taking the test. You can check your own work, but you know. Interesting. So your teacher got twice as much as I got in his solutions. I see, I see. So he did something interesting in his solutions. So here's what he wrote, just to be clear. So he wrote the same thing, right? He wrote the 1/2 the integral of f squared minus g squared divided by the mass. But then mass is really area, and then that 1/2 he pulled out and put it in the denominator. So that's why his integral on top. Really, well, here's what I've done instead. So what I'm getting, instead of getting 16/15 over 2 over whatever the denominator is, I'm getting 8/5, 8/15 over my area, which was, I forgot what it was, 4/3, which still is going to end up being 2/5. So same answer, just a slightly different way of writing it. Yeah. Yes, in this case. So the thing is, really, it's not that we're calculating mass, it's that we should be using different language and saying area. But the problem is when we talk about the center of mass and you don't have a given density, we still just kind of keep saying mass, even though we really do mean area. So yeah, you're right. We should be talking about area. And that's certainly what your instructor wrote, right? He changed mass to area right there because we're talking about a centroid. Yeah.
The formula about is like was doing that division, and like with that formula, he's already getting the y bar. Yeah.
Well, right. Yeah, he's writing 1 divided by the mass. Yeah, exactly. Yes, he's writing the formula for y bar. Whereas I prefer to write the formula for mx, get a thing, and then I already know that the mass, the area is 4/3, and then just divide them.
And if we were given not constant density, but everything is the same font.
Right. Then you have to put that density in your integral and it becomes more complicated. But yes, that's the idea. Other questions about this monstrosity? Yes.
Why?
Sure. So, well, in fact, let's calculate it. So if we're going to calculate the center of mass for around the y-axis, so if I want to calculate my, what I'm doing is I'm essentially saying and it's not that bad to calculate. So now for this strip here, this strip is all a distance of x away from the y-axis. So my lever arm is x, and my function, well, I should say the area of my strip is just my height times my thickness. But now check this out. This is where you get to use one of the other cool facts. That function isn't even. but it sure is odd. If you integrate from -5 to 5 of an odd function, or -2 to 2, or negative something to something, that should definitely be 0. And it is, right? If you integrate this, you get x squared over 2 minus x to the fourth over 4 from -1 to 1, which is 1/2 minus 1/4 minus 1/2 minus 1/4, which is 0. But to answer your question more generically, when we see symmetry, we can imagine that, again, with uniform density, if you were to cut this little piece of, cut the shape out of like something that was somewhat stiff, like cardboard, and could balance it, it would balance on a point that had half of the area on the left and half of the area on the right. So since we see the symmetry of the shape, we can automatically assume, well, yeah, my center of mass has to be somewhere on the y-axis. And the only part we have to really find is how high or low it is. Yeah.
How is this one on?
Well, it's excellent question, because here I ended up multiplying by x because I'm going around the y-axis, not around the x-axis. Whereas in this previous one, I had to multiply by essentially a y thing, which was how high the center of the rectangle was, which kept it being an even function. I will also say, if your instructor gives you a shape like this, they expect you to abuse the fact that it's symmetric. They do not expect to see any of this work. They're be like, yeah, of course they're going to be like x bar is 0 by symmetry. That is for sure what he expects to see. So if you see a symmetrical shape and you're asked to find a moment around it, use the symmetry if there is symmetry. So how do you know your function was even if you didn't have a diagram picture of it? So here's how you tell if a function's even or odd. So for our original function, f of x equal to 1 minus x squared squared, we know it's even because f of negative x, which is 1 minus negative x squared squared. Well, negative x squared is just x squared, and that function is the same as what we started. So this shows it's even because f of negative x is equal to f of x. On the other hand, this other function here, g of x equal to x minus x cubed, we can show is odd by seeing that g of negative x, which is negative x minus negative x cubed, is negative x minus negative x cubed. I know I said the same thing, but it looks different, which is just negative x plus x cubed. And then negative g of x is negative x minus x cubed. If we distribute that, it's negative x plus x cubed. And those are the same. So to show something's odd, you show something's odd by showing that g of negative x is equal to negative g of x. That's how you do it if you didn't have a graph. I need to grab a little more water because might not. All right. Now we'll look at the next question. Much. So yeah, again, can't emphasize enough that if you see symmetry, you are meant to use it. But this problem goes on, right? Yes. Volumes. Okay, there are some volumes here. Good. So, reminder, we just found that for this region, that the center of mass was 0, comma, I forgot what the other one was. 0, comma, I didn't even write it over here. Maybe I should have written it. It was 8/15 divided by 4/3, which is 2/5. I do think it's worthwhile to think about why your answer is right. So notably here, this shape, which goes from a height of 0 to a height of 1, more of the area is on the bottom than on the top. So you would expect the center of mass with the centroid to be below the halfway mark. So if I was getting something that was bigger than 1/2, I would be worried. Fortunately, I didn't. I got 0.2 fifths, and 2 fifths is certainly less than a half. So that reassures me. I'm like, okay, these numbers make sense. This seems reasonable. So someone asked if we had some shape that had X bar or something that wasn't zero or not symmetric. So we'd approach it just like we actually approached it by doing the integral of X, which is your lever arm, multiplied by your height times your dx. So just as a quick refresher here, in terms of X, for moments around the y-axis, it's the integral of X times the area of your strip, which is the height of your strip times the width of your strip. And then for the moment around the x-axis, it's the worst thing. It's the 1/2 the integral of your top function squared minus your bottom function squared. Again, that is specifically if you are doing things in terms of x. You're doing it in terms of y, they interchange. So if you wanted the moment around the y-axis in terms of y, it'd be the integral of 1/2 times your r of y squared minus your q of y squared. And your moment around the x-axis would be your integral of y times whatever your further function was, r of y minus q of y. So just in terms of y instead of in terms of x. Okay, back to the question at hand. Find the volumes of the solids of revolution obtained by revolving the given region about each of the following. So we're first going to revolve around the x-axis. Now, if I wasn't being a careful reader and just stopped reading right there, I would start setting up the integral for volume around the x-axis using the disk method probably. I would say, cool, the volume is going to equal the integral from -1 to 1 of pi times my radius squared. And I might be satisfied with that because I've already done that that integral already, right? We did the integral of 1 minus x squared already. So I'm like, cool, that seems fine. But there's more to read here. First of all, there's going to be other lines. And second of all, it says to use A and B to do part C. So even though this would be fine to do, and actually if we look back at the work we did already, the integral of 1 minus x squared, I forgot I have a 1/2 in there. I think it's like 4/15. We can find it. Really what I want to point out to you is it's the same either way, but to show you how much easier it is to do it the second way. So it's going to be pi times the integral of 1 minus 2x squared plus x to the 4th dx. Okay, I'm going to do the thing I've done every time with the even function here. That's going to be 2 pi times the integral from 0 to 1 of 1 minus 2x squared plus x to the 4th dx. That's going to be 2 pi times. All right, I'm going to skip this. I know that when I integrate this, it's going to be x minus 2x cubed over 3 plus x to the 5th over 5. And then when I plug in 1 and 0, I'm just going to get 1 minus 2/3 plus 1/5 minus 0 minus 0. That's going to be 2 pi times 15 minus 10 is 5 plus 3 is 8. So I should get 16 pi over 15. I hope. Let me check my work before I do the other way. Cool. Or do what you're actually meant to do here, which is use Pappus's theorem, even though it doesn't say that, but the hint is that we're supposed to use the center of mass. And the Pappus's theorem says that if you want to find the volume of something, the volume is equal to the area of the region times the distance it travels. Distance the center of mass travels. So if you think about the center of mass getting revolved around the x-axis, it's essentially going to take this loop that goes around this way. And the distance that loop is just the circumference of a circle with a radius of 2/5. So this distance here is going to be some area times the distance traveled, which is going to be 2 pi times a radius of 2/5. We already found the area of that region. I think it was 4/3. So we have 4/3 times 4 pi over 5, which, yep, still yields 16 pi over 5. So for any question like this, where you've already found the area and the center of mass, if they're asking for volumes of revolution, you should not be using the disk or the washer or the shell method. You should be saying, cool, it's my area, which I already found, times 2 pi times whatever the distance or length between your radius and axis of rotation is. In other words, the radius of this circle of revolution. Okay. Question? Well, so I'm just thinking about how far that is from the axis of rotation, which is the x-axis. So that distance is 2/5 minus 0. Yeah, it's the distance to it's the y distance. Yeah. On the other hand, if we're going around the line, where is the question here? We're going around the line x equals 1. Well, now if we draw this here, what's the distance to my axis of rotation? How far is it from the point 0, 2/5 to the point or to the line x equals 1? Yeah, it's 1. So basically, if you're going to a vertical line, it's the difference in the x values. If you're going to a horizontal line, it's the difference in the y values. So here, our volume is going to equal our area, which still is 4/3, times 2 pi times our radius, which is just a length of 1. So we should get 8 pi over 3. Go ahead. Oh, thank you so much. You're correct. Yes. So I think your instructor answered a different question in solutions for this part, because his answer is 0. Oh, well, he didn't write that in the problem, did he? Right. So in the problem, at least in the problem I'm seeing, it says around the x-axis and around the line x equals 1 and around the line y equals 1. Right. Now, to me, we don't usually ask about revolving a shape around a line that goes through it. That is very atypical. So I don't know. I don't really have a good. I don't think if you revolve the shape around the y-axis, you're not going to get 0 volume unless you think about the volume revolving on itself as canceling itself out, which just seems like it doesn't seem like a good question to ask. So I would, if you're curious about that, I would say you need to ask your instructor because I'm not sure what he's trying to say by saying that volume is 0. Some of it's positive and some of it's negative. That's okay. Let's move on.
Yeah.
Yes.
If like we would revolve over x equals -1, for example, a radius, we would take it as 1.
So if we went around x equals -1, so the radius should always be positive. So it's the distance between the two things. So in this case, where it's x equals 1, it's 1 minus 0. In this case, if it was x equals -1, it'd be 0 minus -1, which would still be a radius of 1. The reason we're multiplying by 2 pi is because it's a full revolution on a unit, well, on a circle of radius, in this case 1. So it's really the circumference of your circle, 2 pi times whatever your radius is. It's just in this problem, the radius happens to be 1. And then finally, for the third part of this question, which is around the line y equals 1, well, then the distance to y equals 1 is going to be 1 minus 2/5, which is 3/5. So our volume should equal still the area of 4/3 times 2 times pi times our radius, which is in this case 3/5. So we end up getting, let's just cancel those 3's. We end up getting 8 pi over 5. I don't know why he's doing it this way. Like he said, he gave you this hint, and then he's doing this totally different way. I'm so confused. Also, he's getting a very different answer than I'm getting, which is concerning. Hmm. Why are you getting a different answer? Are we gonna have to do the work? Do I need to make sure? Let me make sure one thing here. Let me just go back and see one thing real quick. Nope, our area is definitely 4/3. Sorry, it worries me when this seems like it's meant to be done one way and oh, he updated it. Your answers are right. Thank you so much. Appreciate the assist there. I was about to spend a lot of time doing something that was going to show that he was still wrong. So yeah, that's okay. Call. Yes. So the 4/3 in both of these and in the first part here, this was all the area of the region we calculated in the first part. So the integral from -1 to 1 of 1 minus x squared dx. That's our 4/3. That's so again, for volumes using Pappus's theorem, it's always your area times the circumference of the circle that the center of mass travels. Area of the region. Exactly this. So Pappus's theorem says if you have a volume of revolution, instead of doing it using the shell, washer, or disk method, you can instead say, hey, I'm going to pretend like all of the area is centered there. And then as it revolves around this axis, that area, kind of like think if I just took this piece of paper and like was able to like stick it here and then like have it accordion out this way. Its volume would be the area of the paper multiplied by the distance it traveled. It's just now we're saying instead of the distance being linear, the distance is going to be circular. So we're taking this area of 4/3 and multiplying it by the circumference that the center of its mass is traveling, which is 2 pi times however far that center of mass is from this axis of rotation, which in these problems is different depending on the problem. If you have already found the center of mass, which we had already in this problem, right? That was part two, part B of this problem. So if he sets it, if you like this problem was definitely set up in a way where you were encouraged to use Pappus's theorem here because you're already finding the area, you're finding the center of mass. All you have to do to use Pappus's theorem is find out how far your center of mass is from each of your various axes of rotation. So we could ask the same question again. We can make it more interesting. Say, what if I wanted to go around the line? I don't know. Around y equal to -3. Well, let's see. My area still hasn't changed. It's 4/3. And now my radius from, sorry, I can't quite see that. From down here, from y equals -3, well, the distance, no, the distance between my center of mass and my axis of rotation is, right, 2/5 plus 3, which is going to be 17/5. And so then the distance that center of mass is going to travel is going to be 2 pi times 17/5. And then the total volume is going to be the area, two-dimensional, times the distance, one-dimensional, to get a three-dimensional result of volume, which will be something terrible. 4/3 times 2 pi times 17/5. Who needs to simplify? That's kind of the idea with Pappus's theorem. You find all these pieces and you just kind of, it's kind of like you're gluing them all together to get a final answer. Yeah. Exactly, because it's the circumference of the circle that center of mass is going to travel in every time. I guess, yeah, no, I won't say anything else there. All right, that was a lot. Let's look at the next couple things. So it seems to me like you could probably expect there to be a question where you have to find center of mass on your exam, right? Like, yeah. Oh, thank you. I had not. If you're not enrolled, if you could throw your name on there anyway with your student ID number, I would greatly appreciate it. Because I do keep track of the attendance of all the people that come at the end of the quarter. So let's look at 4a here. Find the improper integral from 0 to infinity of e to the negative x. So in my opinion, if you want to earn full credit on a problem like this, you should start by first writing, unless your instructor has said to do it differently, the limit as b goes to infinity of the integral from 0 to b e to the negative x dx. In this case, this is easy to integrate, right? It's a one-shot integration. But if this was more complicated and required like a u sub or integration by parts, I would do that all off to the side. So be like, okay, I do my indefinite integral. I'm pretending like it's more complicated. I have to do some stuff. And then eventually I get e to the negative x divided by -1 or negative e to the negative x. After doing whatever just indefinite integration I need to do on the side, then I'm going to go back and say, okay, this is now the limit as b goes to infinity of whatever my antiderivative actually is, evaluated from 0 to b. And then you plug whatever this is in there. Just because if it's a more complicated process, you don't want to be writing down the limit along with the integral every step. Now we plug in our limits of integration. We get the limit as b goes to infinity of negative e to the negative b minus negative e to the 0. Now be careful here. I personally would choose to do this. I don't like negative infinity as a power. E to the negative infinity, it's always hard for me to remember that 0. It's much easier for me to remember that this is the limit as b goes to infinity of negative 1 over e to the positive b plus e to the 0, which is 1. And then it's more clear to me that 1 over e to the b is going to get really, 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 really small as b gets very, very large, because my denominator is getting large and my fraction is getting small. So this integral converges to 1. But I think it's fine just to stay equal to 1. Question?
Situation where the limit would like it's where it approaches from the left or right.
You never have to write from the left to the right with infinity, because you can only approach infinity from what side? You might, because there's no need to write approaching infinity from the left-hand side there. You're always on the left-hand side of infinity, right? If you draw the number line, there's infinity. You can't be over here. You're always over here. So you never need to write this. Other questions about this one before we look at the next part, which I have no idea about?
General sum.
Sure. So the first step is just wherever my problem point is, whether it's infinity, negative infinity, or some number in between where the function's undefined, which is not the case here, I take that problem thing, replace it with a letter of my choosing, usually b for the top, a for the bottom, and then I'm taking the limit as b approaches infinity. So that this is still representing the same integral, it's just now I can work with that. So then I said, then I really just did the antiderivative e to the negative x and got negative e to the negative x. But I pointed out that if your integration process is more complicated, you should do that on the side, and then whatever you get for your integral, that's what's going to go in there. So then I've done my integral from 0 to b of e to the negative x. I got negative e to the negative x from 0 to b, and the next step I'm just plugging in b first, 0 second. So basically every step of this process until the very end, I'm ignoring that limit, right? I'm just pretending like it's not there, but you do need to write it. It needs to be there to be correct. So limits there, limits there, limits there. I plug in my limits of integration. So I get negative e to the negative b minus negative e to the negative 0, but negative 0 is 0. So, okay. Simplify a little bit. I prefer to rewrite e to the negative b as 1 over e to the positive b minus minus is plus 1. And then the 1 over e to the b goes to 0 because the denominator is getting infinitely large. Yeah.
For example, with an integration from like 0 to 9,
Uh-huh.
like you have to put limit for the right and stuff. Like
Yes. So for example, if someone said the integral from 0 to 9 of 1 over the square root of 9 minus x dx, then you would rewrite this as the limit as b approaches 9 from the left-hand side of the integral from 0 to b of 1 over the square root of 9 minus x dx. Because 9 is the problem here, right? 9 minus 9 is 0, and 1 divided by 0 is undefined. So 9 is the limit of integration that has to get replaced. And since we're between 0 and 9, we are approaching 9 from the left-hand side. Yeah.
Does it change anything if it's put 9 this time?
Not right. And the reason it's not right is kind of subtle, but it's because you can't approach 9 from both sides, because if you're on the right-hand side of 9, that function is undefined. Right? If x is even the tiniest bit bigger than 9, 9 minus a number that's bigger than it is a negative number, and the square root of a negative number is not real. So, I mean, no, it doesn't affect the process at all, but it is a little bit technically wrong.
So if you ask me if that, you would first find out it converges to like Vancouver. And then you take it from the other side.
No. So this is the whole thing. So we're just going to do this integral. Now this one will diverge. Oh no, this one will converge. Yeah. So you just do the integral as is. There's nothing else to say. So this would end up being the limit as b approaches 9 from the left. The integral of 9 minus x to the negative 1/2 is 9 minus x to the positive 1/2 divided by 1/2 and also by negative 1. So this is going to be the limit as b approaches 9 from the left of negative 2 square root of 9 minus x from 0 to b. We plug in, we get negative 2 square root of 9 minus b minus negative 2 square root of 9 minus 0. Plugging in 9 for b, 9 minus 9 is 0. So that's just 0. And then you get 2 times 3, which is 6.
Why didn't you do that for the infinity, like on the left side?
Because it's not required. Because what side of infinity can you be on? Right? Well, it's actually not the right, right? You can't be further right than infinity. Infinity is as far right as you go. So you never have to say what side of infinity you're on. It's never required. All right, let's look at the second part of the, oops. Let's look at the second part of this here, which is determine whether this improper integral converges or diverges. The integral from 0 to infinity of 1 plus sine of x times e to the negative x dx converges or diverges. My thought here is that we're supposed to use some sort of comparison test. So I would point out that we know that sine of x is always between 1 and negative 1. If I add 1 to that, 0 is less than or equal to 1 plus sine of x is less than or equal to 2. If I multiply everything by e to the negative x, 0 times e to the negative x, which is still 0, is less than or equal to 1 plus sine of x times e to the negative x is less than or equal to 2 times e to the negative x. So then we can say, well, certainly the integral from 0 to infinity of 2e to the negative x dx is just equal to 2 times the integral we just found, which I think was 1, right? Somewhere in my notes there. Yeah, it was 1. So this integral is bigger than or equal to 0. I'm sorry. So, right, this integral, because this function is positive, right? This 1 plus sine x e to the negative x is positive. So we can certainly say that the integral of 1 plus sine of x times e to the negative x is less than or equal to 2 and bigger than or equal to 0. I wonder what he says in his answers here. I'm curious, because I feel like there's something I'm failing to say here. How do these things get so out of order? Good question. Oh, right here. Okay. So we just get to say it converges. Yeah, I guess that's fair. All right. Yeah. So if your integral is less than or equal to an integral that converges, it is also convergent. Yeah. Yep. You could write the same problem and replace sine with cosine, and it will play out the exact same way. Because cosine also has the same bounds being between negative 1 and 1. So yeah, so typically with sine or cosine, you can always say that, and that kind of squeeze theorem type argument or comparison type argument usually works. Well, no, no tangent, not really, because it doesn't have the same bounds. Typically, for problems like this, where you're trying to compare things, sine and cosine are often used because they are less than between -1 and 1.
When it's not sine or cosine, he like takes a function that is like smaller.
Sure. Yeah. So here is a question I would ask if I felt like being a dick. Show that this converges or diverges. Now, I'm not doing the kind thing here of helping you set this up. So, in fact, I should be a little more specific here. So that that converges or diverges. So what's the trick that I'm not telling you? Well, it's this. E to the negative x squared is less than or equal to e to the negative x on the interval from 1 to infinity. Does that seem plausible? Does that seem right? Let's see. If I rewrite this as 1 over e to the x squared, and this is 1 over e to the x. So if I plug in something like 3, is 1 over 3 squared less than 1 over, sorry, is 1 over e to the 3 squared less than or equal to 1 over e to the 3? Is that right? It is. So it is true that e to the negative x squared is less than or equal to e to the negative x on that interval. And then you can just say, well, great. Then e to the negative x squared is between e to the negative x. And it does have to be positive for this to work, or non-negative, say. And then we can say the integral from 1 to infinity of e to the negative x squared is less than or equal to whatever this integral is, which isn't the same as the one we just did, but it's close, which converges. That's a question that's easy to answer if you know the trick and hard otherwise. Because famously, this function cannot be integrated. So the thing about a trick is you really can't summarize it because each trick is kind of its own thing. This trick is just knowing the fact that e to the negative x, first of all, the e to the negative x squared cannot be integrated. And so you have to compare it to something to show it's either convergent or divergent. This definitely converges because it is smaller than a function that is convergent on the same interval. But that would be, I could see asking that question on the test. Although I feel like he usually likes to build you up more. Like he likes to kind of write questions with multiple parts that seems like they build up to a certain result. So it seems unlikely, but not impossible. Okay. I could also see asking one like the previous one where it was had like a finite number as your limit, like the 0 to 9 one that we did. Like that's also on the table. Let's look at this last question he's asking, which is also another differential equation. Or I think it is. It looked like it from looking at it, but I should look at it closer. Oh no, it's definitely not a differential equation. So find dy dx at t equal to 1 if x of t equals t e to the t and y of t equals t plus sine of pi t. So this question really is, do you remember the formula for dy dx using parametric equations? So we have to remember that dy dx is equal to dy dt over dx dt. Which it should look like the dt's could cancel and you would get back where you started. That's how I remember it. And then we calculate. So dy dt is going to be 1 plus cosine of pi t times the derivative of pi t. And dx dt is going to be, we have to use the product rule, 1 times e to the t plus t times the derivative of the t. And then we shouldn't simplify this at all. We should just plug in t equal to 1. So we're plugging in t equal to 1, we're plugging in t equal to 1, plugging in t equal to 1, and we're getting 1 plus cosine of pi times pi over 1 times e plus 1 times e. And again, this is technically a correct answer. We could leave it here. The only amount of simplifying you can really do is, I guess, two things. E plus e is clearly 2e, and cosine of pi is -1, so this numerator is actually 1 minus pi. But he doesn't even do that. He just leaves this. Oh yeah, well maybe he does. It's hard to tell. It's hard to tell with his cutoff. What if he asked you to find the second derivative? Second derivative is a little bit trickier. So if I want to find d squared y dx squared, it is the derivative with respect, do I remember what it is? It's d dt of your dy dx over dx dt. So the way I think of it, it's the same formula as the first derivative. It's just you're replacing y with y prime. You're saying d squared y dx squared, which is really just the derivative of y prime with respect to x, is equal to the d dt of your y prime over dx dt.
So we would take the derivative of what we found and divide it by the.
Right. So you'd have to take this monstrosity here, differentiate it using the quotient rule, which is not the best, which is probably why you wouldn't get asked this, and then divide it by e to the t plus t to the t. So yeah, so writing it out very, very, very generically, it's the derivative of 1 plus pi times cosine of pi t over e to the t plus t e to the t. Derivative of that divided by dx dt, which is still just e to the t plus t e to the t. But yeah, it's not a very good test question because it gets real messy. Question. I mean, I don't think I could just because I mean there's so what does he give you though? Because right, does he tell you what he's going to give you on your like what kind of formulas he's going to give you?
He gave us the integral table
Okay.
and.
I mean, I'd certainly put the formulas for the moments in the center of mass. So, which we already kind of wrote out. Let's see, let me look real quick here at one thing. So let's see, just going quickly down the list. So work is equal to force times distance. And I would remind myself that force is just another name for weight. It is measured in either newtons or pounds. Yeah, work. I might also remind myself that fluid force due to pressure is going to be the area of your thing times the depth of your thing times the density of your thing. I know I sounded like there was more to say there. That's it. That's all there is to say. Those three things multiplied together. And then of course you're integrating that. Yes, the formulas for the moments, my being the integral of x times your top function minus your bottom function, and mx being the unfortunate 1/2 times the integral of your top function squared minus your bottom function squared. You are squaring before you're subtracting. And then I guess some of these differential equations or some of these parametric equations. So like exactly that dy dx is equal to dy dt over dx dt. And that d squared y dx squared is equal to the derivative with respect to t of whatever your dy dx is over dx dt. Where literally that is coming in there like that. I mean, there are other parametric equations things. He could ask you about area, right? Area parametrically is equal to the integral of y of t times x prime of t dt. And I don't really feel like we spent enough time talking about that for it to be as plausible. Yeah. What time's your test tomorrow?
3.
3. All right, I'll be in C class, no, not C class tomorrow from 1 to 4. So if you have questions before your exam tomorrow, I'll be available there from 1 to 4. Obviously 3 to 4 doesn't help you, but no, I didn't see that. That's a good question. My papers are all over the place here. 1 second, sorry. I mean, C class, it's El Centro. It's the Center for Chicano Latino Academic Student Success. It's up above the coffee house in the MU. So if you look at the outside stairs, by where the flagpole is, you just go up those stairs and you look to your left. And it's right there. And there's like a big sign. Yeah, you're right. I didn't see anything about exponential growth or decay on here. Right? I'm not like missing it. But that definitely was the thing. Yeah. No, I mean, certainly he could ask about it. But to me, that's really just kind of it's a small little subset of the differential equations content. And he probably, I mean, like most of them, he probably was like, well, they did that in 21A already. So, oh yeah. I'm interesting. Where on the website? I'm curious.
It's the-
Turn 3. You should expect it. At the bottom.
Oh, at the bottom. Yeah. I mean, he could ask about it. It's certainly possible. I mean, I would say for exponential decay or growth, it's really, I mean, usually you're just kind of given some data points and asked to find the model, which is like finding the solving for C and your K and your CE to the KT kind of thing. I suppose he could phrase it in a way where like he could tell you something like you have, dy dt equals 5y, where y of t is the amount of radioactive material. And then also tell you that we know that like y of 0 is equal to 100 grams and y of 20 is equal to 60 grams, and then ask you to figure out what y of, I don't know, 30 is. And the thing that's I'm kind of hiding doing it this way is that we know that we're going to get from this equation that y is equal to CE to the 5 times t. That's what that 5 is doing. So basically, that 5 is your k in your y equals CE to the kt. So I could see maybe phrasing it that way to try to make it more challenging, but I don't know. I don't want to say there won't be one because I don't know. It wouldn't be what I would be looking for, but yeah, I think so. Good luck tomorrow. I hope it goes well. Yes, totally fine. Awesome.
So is there any chance I could be added?
Of course. Yeah. Just maybe make a little red mark next to it so I know who to add.
Thank you so much.
You're very welcome.